Hi everyone. So in today's video, I am going to discuss about torque on a current carrying coil placed in uniform magnetic field. Okay, uniform magnetic field. So here we have this coil, this yellow color coil. Okay, and it is placed in uniform magnetic field, denoted by these parallel lines, parallel arrows. Strength of the magnetic field is B. It is uniform. So everywhere the direction and the magnitude is same. Okay. Now this yellow color coil carries current I. Okay. Now when we are observing from this side, the current is flowing in anti-clockwise direction. Now see, the magnetic field is drawn on the plane of the board, and the plane of the coil makes an angle theta with the direction of the magnetic field. Okay, so magnetic field is like this, plane of the coil is like this. So plane of coil, it is making an angle theta with the direction of magnetic field. Okay, acha. Now we have to calculate the expression for torque. Okay, now we know that torque we calculate by first calculating the force. Okay, see overall what is the net force? See, force on a current carrying conductor placed in a magnetic field, it is given by F equal to IL cross B. Okay. Now see, this L is a vector quantity. Okay. Vector quantity means you have to measure this length from initial position to final position. That is the shortest path from initial position to final position. So now, since this is a closed loop, so value of this L, it is going to be 0. Now Since L is equal to 0, so this implies this force is also 0. But this is the net force on the current loop. So net force on this loop, when it is placed in a uniform magnetic field, it is 0. Okay, but net force does not mean that the torque is going to be 0. Okay, let us see that concept. Like see, I can divide this loop. Into 4 parts. Okay, PQ of length L. So this is a rectangular loop of length L, breadth B. So PQ of length L, then QR of length B, then similarly RS part and SP part. So for each part, we will calculate the force separately. Okay. So first, let us see the force on, say, for SP. Okay. Now SP, this is S, this is P. Current is flowing like this in the downward direction. Strength of the current is I. Okay, and this is the direction of the magnetic field. This is B. This angle is theta. This angle. Okay, this angle is theta. Now, in the expression for force, F equal to IL B sin theta. This is the magnitude of the force. Now, this theta is the angle between L and B. See, vector form, it is F equal to IL cross B. So this theta is the angle between L and B. And how to get the direction of L? L is always in the direction of flow of current. So here current is flowing in this direction. So that means length is also in this direction. Okay. Acha. So, and this is the direction of the magnetic field. So when we are talking about this angle, so here that angle is this particular angle. Length is in this direction because current is flowing in this direction. Magnetic field is in this direction. Theta is the angle between L and B. Okay. So we are talking about this angle. So this angle is pi minus theta. Okay. And see, this breadth is B. So this length, this part is B. So this is B, length of SP. So force on this part, FSP, it will be equal to I, length is B, strength of the magnetic field B, okay, sine pi minus theta, sin pi minus theta. Okay, so this is sin pi minus theta is sin theta, so FSP is equal to I dP sin theta. Okay, now this is the magnitude of the force on this part. Now what about the direction? Direction is, see, current, it is flowing in this direction. Okay, it is flowing in this direction, and magnetic field, it is in this direction. So if we use the cross product rule, see, F equal to IL cross B, so force is in the direction of IL and IL cross B. So that is, force is in the direction of L cross B or IL cross B, because I is with L is in the direction of I. So current is flowing in this direction, magnetic field is in this direction. So if we use right hand curl rule, IL cross B, that is, force will be in the upward direction. So here the force will act in the upward direction. This FSP. So this force is in the upward direction. Okay. So this is force on part SP. Now let us see what is the force on segment QR. Okay. So QR, this is Q, this R, current is flowing in this direction, I. Okay. This is the direction of the magnetic field. So this is the direction of magnetic field. This angle is theta. So here theta is the angle between L and B. Length is in this direction because current is flowing like this. Magnetic field is this. So now theta is no problem with theta. Finding the value of theta. So FQR is equal to I B P sin theta. This length is also B. Now what about the direction? Now current is going in this direction, so length is in this direction, because current and length, they are in the same vector, same direction. IL, L is in the direction of I. So this is L, this is the direction of, so length is in the inward direction, B is in this direction, so IL cross B will be in the downward direction. So force on this part, it will be in the downward direction. So this is F QR, it is in the downward direction. So this is in the downward direction. Okay. Now, as you can see here, for SP part, suppose this is the SP part, and this is the QR part. So here the two forces are equal in magnitude. The two forces are equal in magnitude. Okay, and they are acting in opposite direction. So this force, they are equal in magnitude, they are acting opposite direction, and they have same line of action, both the forces. Their forces acting along the same line. So there will be no translation, and there will also no torque. Okay, so these two forces will cancel. So one force is acting in the upward direction, one force is acting in the downward direction. So they will cancel, and net force is 0 along the vertical direction. Okay, net force 0 along vertical direction. Okay, and there will not be any torque also, because both the forces have same line of action. Okay, so no torque as the two forces have same line of action, Okay, same line of action. So for this part, F, SP and QR, we have seen the forces, they cancel each other. Okay, and they don't produce any torque also. Now let's see what happens for PQ and RS. Now for part PQ, so this is P, this is Q, current is flowing in the downward direction. This is the direction of the magnetic field. This angle is 90 degree. Okay, so here force will be F equal to force on PQ. So F force on PQ part, it will be equal to I, length is L, B sin 90 degree, Okay, angle is 90 degree. So F PQ is equal to I L B. Now what about the direction? So here we can use Fleming left hand rule because magnetic field is perpendicular to the length of the conductor. So current is flowing in downward direction. This is the direction of the magnetic field. So force will be in the forward direction. So here force will act in the forward direction. So forward direction means dot. Okay. Now what about the force on part RS? This is R, this is S. Current is flowing in the upward direction. This is the direction of magnetic field. So again here the angle is 90 degree. Okay. So force will be maximum and force will be FRS is equal to magnitude of the force FRS equal to ILB sine 90 degree. Okay. So FRS is equal to ILB. And what about the direction? Here current is flowing in the upward direction. This is the direction of field. So this thumb is in the direction of the force. So force will be in the inward direction. So here force is acting in inward direction. So these are the two forces and their direction. Okay. Now again, as you can see, the two forces have equal magnitude. One force is acting in the forward direction, the other force is acting in the backward direction. So they are acting in opposite direction. So again, net force is 0. Okay, here also net force is 0. But here what happens? See, if this is the coil, here the force is acting in the forward direction. Here the force is acting in the backward direction. So this will produce a torque and it will cause the coil to rotate like this. Here force is acting in this direction. So one force is having this line of action, the other force is having this line of action. So the two forces have different lines of action. So hence they will produce a torque. Okay. So next let us calculate the expression for the torque. Now if this coil is observed from above, okay, so now we are observing from this side. Now if we take the camera from this side to this position, okay, and we observe this coil from above, we will have this view. This is S, this is P, and this is the direction of magnetic field. This angle is theta, and for this part force is acting in the forward direction. So force is acting in the forward direction. So this is F PQ. Here force is for S, this part force is acting in the backward direction. So this is FRS. Okay, both the forces are equal in magnitude. So FILB, FILB, but they have opposite direction. Okay, so here FRS it is equal to FPQ. Forces are equal in magnitude. They are acting in opposite direction. So FRS, vector FRS equal to minus FPQ. They are acting in opposite direction. So they will form a couple, producing torque. Okay. Now we know that torque due to couple, it is tau is equal to either force, product of either force and perpendicular distance between the two forces. Perpendicular distance between two forces. Okay. So here these are the two forces. B is the length of the segment SP. So if we complete this right angle triangle, this angle is theta, so this angle will also be theta. So if this is B, this will be how much? It will be b cos theta. It will be b cos theta. So that means the perpendicular distance between these two anti-parallel forces is b cos theta. So tau is equal to either force. So you can take any one force, ILB into b cos theta. ILB into b cos theta. Now this is length, this is breadth. Length into breadth is the area of the coil. So tau is equal to IAB cos theta. Now current into area is magnetic dipole moment. So tau is equal to MB cos theta. Okay, so this is tau is equal to MB cos theta. But see, theta is not the angle between M and B. Theta is not the angle between M and B. Theta is the angle between plane of coil and direction of magnetic field. And M is perpendicular to the plane of the coil. So, and moreover, if I write MB cos theta, it looks like it is M dot B. But torque cannot be equal to M dot B because torque is a vector quantity. It's not a scalar quantity. Okay. So what we will do, we will draw one normal to the plane of the coil. Okay. So this is normal to the plane of the coil such that angle between normal to plane of coil and direction of magnetic field is alpha. So alpha is the angle between normal to plane of coil and direction of magnetic field. Theta is the angle between plane of coil and direction of magnetic field such that theta plus alpha is equal to pi by 2. Theta plus alpha is equal to pi by 2. So theta is equal to pi by 2 minus alpha. So if you make that substitution over here, we have tau is equal to MB cos pi by 2 minus alpha. Cos pi by 2 minus alpha. Cos pi by 2 minus alpha is sin alpha. So tau is equal to MB sin alpha. Okay. Now we can write this as tau is equal to M cross B. Tau is equal to M cross B. Okay. So here, so torque is a cross product of magnetic dipole moment and strength of magnetic field. Now this expression is quite similar to what we have seen in electrostatics, like torque on electric dipole in electric field. It was tau is equal to P cross E. Tau is equal to P cross E. This was in electrostatics. Okay. This was the torque on the electric dipole. Here it is the torque on the magnetic dipole. This is electric dipole moment. This is magnetic dipole moment. This is electric field. This is magnetic field. So expressions are quite similar. Okay. So now we have got the expression for the torque. Okay. Torque equal to M cross B. Okay. Now tau is equal to MB sin alpha. We have, you can write like this, or tau is equal to MB cos theta. For numerical solving, you can use either of the two formulae, provided you know what is the meaning of alpha and theta. Okay. Now, for theta is equal to 0 degree, alpha is equal to 90 degree, because theta plus alpha is 90 degree. So in that case, torque will be maximum and it will be equal to MB. It will be equal to MB. Okay. Now, for alpha is equal to 0 degree, theta will be equal to 90 degree. Okay. For alpha is equal to 0 degree, torque it will be equal to 0. Okay. So torque will be 0 for alpha is equal to 0 degree. Again, for alpha is equal to 180 degree also, torque is 0. That means if see, alpha is equal to 0 degree means this angle is 0 degree. Alpha is this angle is 0 degree, or theta is 90 degree. So that means if the coil coil is placed perpendicular to the direction of magnetic field, okay, in this direction, then the torque on the coil will be 0. When the torque is 0, we say that the coil is in equilibrium. Coil is in equilibrium, okay. But this case, alpha is equal to 0 degree, that is, alpha is equal to 0 degree means, see, this is the direction of the magnetic field. Alpha is equal to 0 degree means coil is placed like, so this normal is in the direction of the magnetic field. We know that magnetic moment is in the direction of normal, so this is M, okay. So this is M, so M and B, they are in the same direction, alpha is equal to 0, torque equal to 0. M and B, they are in anti-parallel direction, M in this direction, B in this direction, again torque will be 0, okay. But this condition, when alpha is 0, that is M parallel to B, torque is 0, M anti-parallel to B, anti-parallel to B, here also torque is 0. For both cases, torque is 0, but M parallel to B implies stable equilibrium. See, torque equal to 0 means equilibrium, but equilibrium, as we know, it is of two types. So M parallel to B means stable equilibrium, and this is M anti-parallel to B implies, this implies unstable equilibrium, okay. So now we know what is the expression for torque, okay. Torque can be written like in terms of sin alpha or cos theta. Alpha is angle between normal to plane of coil and direction of magnetic field. Theta is the angle between plane of coil and direction of magnetic field. Maximum torque is when theta is equal to 0 degree, alpha is equal to 90 degree. Okay. Alpha is equal to 90 degree means magnetic moment is perpendicular to magnetic field. When alpha is equal to 0 degree, magnetic moment is parallel to magnetic field. Torque will be 0, it is stable equilibrium. When alpha is equal to 180 degree, that is magnetic moment is anti-parallel to direction of magnetic field. Torque is again 0, but this is unstable equilibrium.